Okay, turns out I gotta wait for the YouTube is taking forever to upload my other parts, so I'm just gonna keep on going. Alright, so we're looking at weak acid, strong base curves, and we're also gonna look at weak base, strong acid. So when you're doing a titration that involves weak acids or weak bases, your other substance, typically your titrant, is the substance that is strong. Okay, you can't have a weak substance titrating with a weak substance because you end up just having equilibriums fluxing back and forth. You have to have one that is strong and one that is weak. So a couple of differences here. So we have equivalence point. So you're going to notice your equivalence point will not be at 7 at this point. So equivalence point is when your moles of acid are equal to your moles of your base. This is still true. However, when you have a weak acid, your product ion that's made is going to be undergoing an equilibrium with water. Okay, so that's what's causing this influence. So essentially, it's going to become a more basic solution because you have to actually add more in order to neutralize it. Okay. So when you are looking at this, you're also going to notice that there's this, it's not as much of a sharp incline as the strong acid, strong base was. You have this area called the buffer region. Okay, so buffers we looked at in chapter 6. Basically, this is where the pH is not changing a whole lot. So you're adding more base as you move along here, but the pH is not changing dramatically. Okay, and this is seen when you have an equilibrium process. So the pH of the solution halfway to the equivalence point, which is actually what they're showing you right here, is when your pH is equal to your pKa. Okay, we're going to look at that in a bit. Okay, so I would say this is an important thing to remember. So you essentially have before equivalence point, halfway to equivalence, or I should say before the halfway point, after the halfway point, before the equivalence point. This is where your buffer region is happening. So this is where you have your +1, -1 range. And when you have the halfway to equivalence point reached, your pH is equal to your pKa. Okay, so what happens here, and I mentioned this to you, is the product salt is going to undergo hydrolysis. So you're not going to have ions that are doing nothing. You're going to have an ion that's actually creating an equilibrium with water. Right? So this is just to show you the comparison of the two ranges, right? So here, right, 7 is the equivalence point of the red line, whereas this is the equivalence point of the blue line. It's hard to see because they're overlapping each other, right? You also have this buffer region where it's steadily going up, but it's not very dramatic about it. It's just to show you the main differences between the two. Okay, so we're going to do one at a time here. We're going to do 1A on this page, and then we're going to do 1B on the next page, okay? So it says, calculate the pH of a solution produced when we have this volume and this concentration of sodium hydroxide added to volume and concentration of now we have a weak acid. Is this value less than or greater than the pKa for, that's methanoic acid? Okay, so let's write out our reaction, right? We have NaOH reacting with HCOOH. This is going to make water and sodium methanoate. Okay, now this is the ion that I'm talking about that will later on do equilibrium. Okay, so we have, let's look at the initial. So we'll do our initial here. Okay, just to determine what's going on. So we have to do the same thing as usual. We have to find our C2 for both the acid and the base, right? I'm hoping you're okay with me not showing the calculations for this, but we're doing 9 times 0.2 divided by 29 here, right, to get the C2. So this C2 should be 0.06207. And the C2 here is going to be 20 times 0.2 divided by 29. So the C2 for our acid is 0.13793. And of course, we start with a 0 here. Okay, so your change. So limiting reactant here is going to be our base. So this is going to completely react, right? But we will have some of this remaining. So if we do 0.13793 minus 0.06207, we get 0.07586. Okay, now in the strong acid, strong base calculations we just did, we kind of stopped here, right? And then we looked at the pH. But we have to remember this ion is going to have an impact. So actually when we react those, we're actually producing the product amount in that same amount. So we have 0.06207 on our product side. Now, why is this important? Because our equilibrium that is happening in solution with our COOH, because we have some of this still remaining, we have an equilibrium with that weak acid. Right, so this is making H3O plus and COOH minus. So our Ka expression is going to be whatever the hydronium is, we don't know that, our COOH, which we do have, right, over our HCOOH. Okay, so essentially to find the pH, we can find it by getting the hydronium concentration here. So we have our Ka value, 1.8 times 10 to the negative 4 is equal to, so hydronium I'm just going to put as an X. Our conjugate base ion we have here 0.06207 over our remaining weak acid that's there. Okay, so if we figure out our X is 2.1999 times 10 to the negative 4. So this is our hydronium. So we can get the pH of the solution after those two things are mixed by doing negative log of that, which gives us 3.658. Okay, now, the question didn't ask us for that, actually. It asked us, is the value less than or greater than the pKa for HCOO3? So we have our Ka. So pKa is equal to negative log of the Ka, which is 3.745. So that means this is less than the pKa. Right, so what that means is we're not at the halfway point to equivalence yet. Because at the halfway point to equivalence, those two should be the same. Okay, so for part B, so we did part A already. Part B, calculate the pH at the equivalence point of this titration. Okay, so I'm just going to go over here and actually I'll just rewrite it out again. Plus water. Okay, so because we have equivalence point, the concentrations are the same. So what that means is you would be adding the same number, the same amount, right? So equivalence point would be 20 mils of the 0.200 moles per liter of NaOH, because the moles of your acid have to equal moles of your base. So because the concentration is the same, that means equal volumes, right? So we still have to do the C2 business, right? So the C2 in this case now would be, right, 20 mils times 0.2 over 40 mils, right? 0.2 divided by 40. Right, so it's going to be 0.1 moles per liter. And actually this is going to be the exact same because that's the whole point, is that it has the same number of moles. Okay, so we start with 0 of this. So because they're equal, that means there's going to be no reactant left, right? But we are making that product. So now there is no weak acid equilibrium because the weak acid is completely gone. However, this 0.1 moles per liter of that weak base conjugate that has been made is going to hydrolyze with water. Right? So we have an initial concentration of 0.10. So this is a weak base equilibrium. So it's going to be Kb. Right? We start with nothing here. We're going to do minus x, 0.1 minus x plus x plus x. So Kb, remember we want pH. So the whole purpose of this is we want to find out that hydroxide. So this is going to be x squared over 0.1 minus x. Kb, guess what? We got to do a little side calculation for it. I know you love it. So Kb is going to be Kw over the Ka of, this is the Ka for the conjugate, which is HCOOH. So your Kb value after you calculate that should be 5.56 times 10 to the negative 11. The 100 rule for sure will work here. Okay. So that means we're left with 5.56 times 10 to the negative 11 is equal to x squared over 0.1. Okay, so our x works out to be 2.358 times 10 to the negative 6, which is our hydroxide, which means we can find our pOH by doing negative log of this, which is 5.6275, and then the pH you do 14 minus that. So, what are we doing for sig figs up here? The concentrations are 3. So let's say 14 minus 5.6275. 8.372. Okay, so notice the equivalence point, right? It's higher than 7.